75%. And patients without lung metastases who underwent complete resection had a significantly worse outcome, but still better than those that could not have their disease completely resected with a median survival of 32.5%. Asynchronous metastases, meaning they developed their metastases distant from when they had their primary tumor, those patients who underwent complete resection again had a significantly better outcome. If you had two metastatic sites that could be completely resected, you get significantly better than, again, those patients who could not have complete surgical resection of their metastatic disease. And that also held true for those patients who had even more than three metastatic sites, meaning like lung, bone, liver, or other organs. What is clear is that you should go in there trying to swing for the fences, meaning that the completeness of the surgical resection is the most important factor that predicts outcome. If you go in and they have 5 metastases and you only resect 3, you're probably not doing that patient a service. So resection of complete metastatic disease was associated with the best outcome in all these different studies. Performance status is also important. It's important to operate on patients who are healthy and doing well. And in this particular retrospective study, performance status was a strong predictor of outcome with regards to metastasis. And then finally, this was a systematic review looking at all of these different studies and the role of metastasis. You can see from all these different bars over here on favored metastasis side that all these studies were able to demonstrate that surgical resection of metastatic disease was associated with an excellent outcome in properly selected patients. So in summary, complete resection, when feasible, I would argue represents the best option for selected patients. It's better than any chemotherapy we have to offer. Incomplete resection remains beneficial, but I would argue systemic therapy probably is a better option than just resecting part of the disease. But we need to keep in mind that metastasiectomy is a reasonable option in patients with solitary or oligometastatic, meaning very minimal metastatic disease, who are good surgical candidates. And so with that, I'll close. I'll be happy to answer any questions that you have, and then we'll take a break for about 15 minutes. Any questions at all? Okay, why don't we take a break for 15 minutes, and then we'll start with the second half of the program. Thanks very much. Thanks all for coming. What I'm going to do over the next 20 minutes or so is talk a little bit about some of the agents that we use for kidney cancer, and then talk a bit about some of the ones that we are using in the front line. Some of these agents that are approved in the front line setting, and one agent that's kind of coming down the pipeline in the front line agent. I think it's important for us to talk first about how do these drugs work, and I know that many of you are seasoned patients, and you've heard this stuff before, but I think it's always good to review. So there's really 3 major classes of drugs that we use for kidney cancer. The first is a blood vessel starting or anti-angiogenic drug. Well, this we have a number that are approved. Sutent and Votrient are very good examples of it. Cabometyx is also an example of it. And the second major class, which you're going to be hearing about from Dr. Gell, are the immune-modulating drugs. And there's the old-fashioned one, interleukin-2 or Proleukin, and then there's the new-fashioned one, an example of which is nivolumab or Opdivo. And the third are mTOR inhibitors and mammalian-targeted rapamycin inhibitors. And when we are treating cancer, increasingly we're realizing that what we're doing is we're treating an organ. We're not treating just the cancer cells. Actually, for the large part, we're really bad at targeting the cancer cells directly. And so a lot of the treatments that we use are either just kind of tickling the cancer cell, slowing it down but not killing it, or working indirectly through other cells, which can we can either decrease their function or we can increase their function. So these anti-angiogenic or blood vessel starting agents do exactly what those words sound like. They will actually target those blood vessels. In cancer, blood vessel cells themselves are actually not cancerous. They're normal cells. They don't have mutations, generally speaking. But what they are is they're new blood vessels that have been generated that are young and immature and are addicted to factors that the tumors are actually producing. So because they're addicted to this and they're more vulnerable, if you block that, then you can actually damage those blood vessels and not the normal blood vessels in our body for the large part, which is why these drugs actually work. Because otherwise, if we were using blood vessel starting therapies and our aorta and our veins and arteries and the normal parts of our body were to break down, this would not be very therapeutic. But because it's affecting the blood vessels of the cancer, the tumor organ itself, then we are targeting that. So these tumors, as they grow, 1 cell, 4 cell, 8 cell, 15, etc., when they're really small, you can actually get nutrients to the middle of the tumor without any major problems. But as they grow beyond a certain size, you can't get the nutrients to the middle anymore, and that's when these blood vessels start forming. So in that regard, these therapies probably only work when there are blood vessels in the tumor. So this micrometastatic or one circulating tumor cell or one tumor cell that's lodged somewhere in a lung or other organ in the body probably won't work that well. But once you have those blood vessels, it'll work better. So the immune agents that Dr. Gao is going to be talking to you about, they work rather differently. So we've known for the longest time that kidney cancer is an immune-responsive cancer, where in some cases we see spontaneous shrinkage, we've seen that interferon and interleukin-2 kind of work, but they don't work as well as we want. And part of the reasons why is because our immune system, as you're going to be hearing, has a set of checks and balances. You probably know of or have heard of or have friends and family members who have lupus or rheumatoid arthritis. Those are examples of our immune system run amok. And so we don't want that either. We don't want our immune system to be overactive. We don't want it to be underactive either. So the therapies that Dr. Gary is going to talk about, they actually will help the T cells, the immune cells that are sort of in between the blood vessels and the tumor cells to wake up, recognize the cancer cell, and kill the cancer these are, if the cancer cells themselves are runaway bus with the gas pedal on full, what they do is they basically take the foot off the gas pedal and slow down the bus, but they don't actually stop the bus or bring it to a halt. Slow down the rate of change. So they're probably the weakest agent of the three, although there's a subset of a small percentage of individuals who derive major benefit from these. So it's a little bit of a background of the different classes of drugs we're using. The one that's most exciting really is where there's the largest growth in immune therapies, and there's far more immune therapies out there now already than we can even design clinical trials for. That means that we're going to have to think differently about how we design clinical trials in the future, because now what we're doing is basically we design a clinical trial around this big imagine a pill, and it's surrounded by a whole bunch of people, and we're basically trying to apply a whole bunch of people to that one pill or drug. In the future, when we get smart enough, we can characterize an individual's tumor better. We will then take that patient and essentially do experiments with saying, all right, characterize the tumor, and then come up with therapies that are really personalized and specific to that person's tumor. And as the tumor changes, because it's always trying to escape what we're doing, we can then alter in a smart way the therapies that we're applying. That hopefully is going to be the way we treat people 10 years from now. So, without taking away from Dr. Gowns's show far more beautiful slides than this, I'll skip these just so that I don't steal his thunder. A couple definitions. Nephrectomy is, as you've heard, removal of kidney. Adjuvant therapy is therapy that we give after we don't see any evidence of cancer, like after a surgical removal after the nephrectomy. Metastatic is stage 4, when you have spread to other organs in the body. Randomized trials mean that basically you have a study where you have a bunch of people, and you then basically divide them into 2 or 3, whatever. You divide them into these 2 groups, and then you let a computer flip a coin and decide which drug one group gets versus the other group. And so that's basically how we figure out when we do trials to make sure that these trials are done in a fair manner or fair testing of the drug. Double-blinded sounds kind of scary, but this means that when you do a double-blinded randomized study, this is when you don't, the doctor nor the patient knows whether or not they're on the experimental arm or whether they're on the standard arm. And the study phases, phase 1 studies, we're basically trying to figure out what the best dose is, what's not toxic. Some hints of effectiveness. Phase 2 is when we move on to figuring out whether a drug shows a signal for a particular group of individuals. And phase 3 is when we're actually proving that that drug is useful for that group of individuals. So let's now talk about treatment for metastatic disease in the frontline setting. Here is a table, which I'll ask you to memorize because I'm going to hand out a quiz after this tape. This is basically the table of the drugs that are currently available for kidney cancer, both in the frontline setting, which I'm going to focus on some first-line therapy, and then second-line therapy. And you see in the second column, there's risk, good or intermediate risk, and poor risk. I'm going to explain what that means, why we're talking about risk factors. And then I'm going to focus on the approved agents, inotuzumab, Eversupin, and Motrin, and I'm going to introduce Cabometyx or cabozantinib as an experimental agent in the frontline setting. And I'm going to briefly talk about commercial. So what are risk models? It's not, whether or not, you're acting risky or more or less risky, but it's whether or not your cancer has a higher probability of resulting in shorter survival versus longer survival. And so these risk models are statistical creations where using a couple of different factors, using things that seem to be associated with better or worse outcome. For example, short time from diagnosis to treatment, low hemoglobin, high LDH, high calcium, less feeling wellness. And then you put those together and you can come up with these models that say that if you have none of those risk factors, you're going to have the best survival. If you have 2 of any of those risk factors,